Alright guys, check this out. In Haskell, the $sign operator can be used to be a handy tool for making your code cleaner and easier to read. And let's check out the square root. So you want to have the square root for 1 plus 2 plus 3. Check this out, that's going to be 2.44. Now you can omit the parentheses and you can do instead square root with the $sign 1 plus 2 plus 3, and that's going to give you the exact same thing. So both expressions are equivalent, but the one with $sign is often easier to read, especially when chaining multiple functions. I love this language. Hey, what's going on everyone? This is BegBrace channel. My name is Amir and welcome to this Haskell programming language course for beginners. This course is for beginners in Haskell, but not for beginners in programming in general. So I won't assume that you're new to programming, right? In this course, I will operate under the assumption that you already have a foundational understanding of programming concepts. So don't expect deep, detailed explanations about basics like data types, data structures, arrays, tuples, objects, loops, conditionals, references, pointers, garbage collection. You get the idea. My goal is not just to cover syntax, but to dive into the mindset of the language itself. I will also finalize this course by creating 2 different applications to demonstrate different concepts. I believe that learning by doing is much more effective than just studying the basics and then forgetting everything. And if you're new to the channel, thank you so much for tuning in. Please consider subscribing to the channel. And for all of my viewers and subscribers, thank you so much guys for your support. I always appreciate your feedback and constructive criticism as always. Leave your comments, questions, and anything else you want to leave. Okay, that was the end of the introduction. Now let's go ahead, jump right into some history lesson. All right, Haskell, what is it? Haskell is a widely used, purely functional programming language. Functional programming is based on mathematical functions. Besides Haskell, there are other popular languages that follow the functional programming paradigm. That includes Lisp, Erlang, Clojure, and the surprise is Python. Yeah, believe it or not. So what makes Haskell so special? It's all about purity, immutability, and lazy evaluation. These features give programming in Haskell a unique flavor that you will soon come to appreciate. Plus, Haskell has a vibrant and supportive community, making it an exciting language to learn and use. As I said, Haskell is a functional programming language that traces its roots back to the late 1980s. The language itself is named after Haskell Curry. This is an American mathematician and logician whose work in mathematical logic and combinatory logic led to the foundation for functional programming. Pretty cool, right? The project kicked off between 1987 and 1990, and this was led by researchers like Simon Peyton-Jones, Paul Hudak, and others. They wanted actually to produce a functional, statically typed language, and in 1990, Haskell version 1.0 was born. By 1998, Haskell 98 was released, which consolidated features and set a standard. The Glasgow Haskell compiler, or GHCI, is a key implementation of Haskell, and it's the main software we're going to use in the course to compile our Haskell programs. Now let's get our hands dirty. Step 1 is to download and install GHCI. This is of course the website haskell.org, and you can click on downloads. And you will find here, so it tells you here, downloads, recommended installation instructions. So for Linux, macOS, FreeBSD, Windows, or WSL2, you can use GHCI up to install GHCI, Cabal install stack, and Haskell language server. I prefer only to, at least initially, to install the compiler. Just don't try to go with Cabal, stack, and all of that. So you will click here. And the installation, so to install on Windows, you can copy this link. You can go to your terminal, paste that in, and hit enter. Now I will not do that because I already have Haskell installed on my machine, but to make sure that you have Haskell installed on your computer, you can type GHCI, which is the Glasgow Haskell compiler, -- version, and you should find something like this, the glorious Glasgow Haskell compilation system version 9.4.8. That's the latest version. Haskell is a compiled language, but also it provides you with an interpreter. So you can compile your program to create executables and run the executables, of course, but also Haskell gives you an interpreter to run your code and test your code. So if you will type GHCI, that's the Glasgow Haskell Compiler Interpreter, which sounds strange. So you can do math, you can create stuff, for example. You can print things. All right, so that's the Haskell interpreter. You can create here for the first steps, and it will show you how to compile your program, how to, run different commands and stuff like that. So that's the user guide, for example, for the GHCI. So let's try that out. Let me just exit. Let's do GHCI help. It's going to give us everything that we need to read. So how to use GHCI, right? Available options, enable verbosity, the main commands, TUI to start the interactive GHCI. So we can actually try that. Can do GHCI TUI. Okay, so that's the interactive mode for the GHCI. And GHCI actually is a tool that makes it easy to install and manage different versions of your compiler. Not only the compiler, but other Haskell related tools. And it's especially useful for Haskell developers who need to switch between different versions of the compiler for various projects. So to quit, I'm going to hit Q, Control L to clear the terminal. Also, there is a playground where you can, test your code and run your code if you want. So if you will hit on run, welcome back Haskell query. So this is the interpreter, as we said, right? But also I want to show you if you want to compile. So let me go to my own folder, and I want to create just a simple file, and I'm gonna call it hello.hs. That's the extension of Haskell, of course. So in Haskell, in any compiled file, the first thing you need to have is your main function, which is the entry point of your Haskell program. So that's going to be main, then double colon, then IO, which stands for input output, and parentheses, open close paren. This basically performs input output actions, which in this case I'm going to use to print a simple string to the console. Then here I'm going to say main equal to a function called put stir line, which means that I want to put a line in a string form and what I want to write. So hello world, of course. And we will save the file and we will exit. And now I want to compile my hello file. To do that, I'm going to use the GHC, the Glasgow Haskell compiler. Then I will compile this hello.hs file. And I want to create an executable output. So that's -o, which stands for output, and the name of the file. Simply, you can call it anything you want. Hello, h, whatever. And if you will list the components of your folder, now you have your executable, you have your Haskell interface, your Haskell extension, and your output. Now go ahead and run your Haskell file. And indeed, we have our hello world printed to the console. Alright guys, so that's it for this quick introduction to Haskell. We have covered downloading GHC, writing a simple program, and running it both as compiled executable and in the interactive environment. Thank you so much guys for watching, and I will see you in the next lesson. Haskell is purely functional programming language. That will come to your mind the difference between imperative and declarative. Functional programming, like Haskell, is declarative. You tell Haskell what the thing is, not how to do the thing. In contrast to imperative programming, like in JavaScript, in Rust, C, C++, all this is imperative. These languages are not functional. In JavaScript, you can use, there are functional features, but it's not functional by default. Besides Haskell, some of the other popular languages that follow the functional programming paradigm, Lisp, I haven't studied or I haven't worked with those languages. But besides Haskell, there is Lisp, there is Python, believe it or not, Clojure, very popular as well. And Haskell is more intelligent than other programming languages such as Java, C++, PHP, etc. Now, the prerequisites, just to move along with me, although it's a tutorial for beginners, I will assume that you have reasonable exposure to any other programming environment. You know what variables are, you know what data types are, how to create functions, loops, if-else statements, Okay, so don't expect me to explain programming more than I will be explaining functional programming and specifically Haskell. Now, I have a video where I've explained how to install the Glasgow Haskell compiler and interpreter. I will leave a link to that video in the description somewhere below, and you can check it out. It's really easy. You will go to the website, copy the command, you will paste it to your terminal, you will hit enter, and that's it. I don't think it's a big deal. But for now, I want to open the interpreter. So this is Haskell interpreter. So back to the conventional and functional programming. In conventional programming, instructions are taken as a set of declarations in a specific syntax or format, right? So in something like JavaScript, you declare a variable, you create a function, you can have side effects. A simple example for side effects is just printing something to the console when you do console.log. This is a side effect of your program. This doesn't exist in functional programming. In Haskell, we don't have any side effects, right? There is no mutation between the input and the output. And that's really powerful. Haskell does not change things. If you will, there is a function, you enter an input, you will get an output. That's it. There is nothing in between. There is no unexpected behavior in Haskell programs in general. And this is very suitable for the banking sector, for example, the finance, because they need to basically have stable results in terms of the finances and, the statements and all of that. It's going to be disastrous if there are some changes in the results. So functional programming, and specifically Haskell, is very suitable for finance and banking, the banking sector in general, creating applications, programs designed or tailored for the banking or the finance sector. Also, it's great for academia. So it's used for, scientific researches, academic researches and all of that. So in functional programming, all the computation is considered as a combination of separate mathematical functions. So you have separate mathematical functions. They are, gathered together, like grouped together and creating your application. We'll see that when we'll come to the module. So it's modular. Haskell, it's called a modular language because each function is considered to be a small application. Right. So this is what is functional programming all about, right? So in conventional programming language, something like C, JavaScript, Java, whatever, you instruct the compiler a series of instructions, right? So it's nothing more than you telling your computer exactly what to do and how to do it. In Haskell, we tell the computer what it is. So you don't tell your Haskell program what to do or how to do, rather you tell it what it is. That's it. So again, I'm repeating that point because it's very important. Haskell programming language is a functional programming language. It's based on functions, on mathematical functions. So let's say, for instance, that I want to create a function, and that function is going to take a number and it's going to return the square number of that number. So let me create this square it takes x and it returns x multiplied by x, right? Now, if you will do square 23, you will get 529. This is an execution of a function. It's basically only function. It's a program. It's a simple program that takes a number and takes an input, returns you an output. That's all what it does. Another thing in Haskell is something called laziness. And by laziness, I mean that Haskell will not evaluate any expression without any reason. So if you're going to give Haskell an array of million, from 1 to million, for example, it's going to be lazy, idle, it's not going to use it unless you're going to call on that array, or you're going to use some function using that array. In other words, when the evaluation engine finds that an expression needs to be evaluated, it's going to create something called thunk data structure. Thunk, T-H-U-N-K. T-H-U-N-K, thunk data structure. This thunk data structure collects all the required information for that specific evaluation and a pointer to that thunk data structure. Okay, and it's also related to garbage collection. I'm going to talk about garbage collection later. So again, this evaluation engine in your Haskell programming language starts working only when it's required to evaluate that specific expression. Other than that, it's not going to touch it. And that's why it's called lazy programming language. Why lazy? Because it's not going to evaluate unless it's asked or required to do so. And let me give you an example. Let's say I want to define an array from 1 to infinity, right? So let me say let infinite list, right? Infinite list is equal to 1 to whatever, to the infinity, okay? If you want to take the first 10 elements from that infinite list, you can do so. And that's using a very interesting function in Haskell called take. So we take the 10 first elements from the infinite list. Oops, I misspelled that. Okay, let's do like this, infinite list, right? Now, again, let's take the 10 first elements. Sorry for that technical error, guys. And there you go. You have a list from 1 to 10. Only from 1 to 10 in that infinite list that originally is from 1 to infinity. It's going to compute elements only when they're explicitly needed. The take is very interesting function. It does what it says, right? It takes whatever is the number of elements inside that list and returns them inside the list. This is a list, right? An array in JavaScript, a list also in Python. Here, for example, you can say true. This is Boolean. You can say here false, right? It's going to return true or false. If you're going to add a string to the list, it's going to yell at you. So if you'll do, this is a string, right? You will have, of course, an error. It's a type error because couldn't match expected type bool with actual type car. So that's interesting. Just I wanted to show you that. The next characteristic of Haskell is modularity. So any Haskell application is nothing but a series of functions, like I've told you in the beginning of this video. So you can say that a Haskell application is a collection of numerous small applications. They are all combined together, forming your whole application. So each function is considered to be an application in itself. Let's say that I want to have a double that takes x and multiplies x by 2. Also, let me have a number that's being incremented by 1. So let's call it increment, right? That's x, and that's, basically adding x plus 1, incrementing x by 1. So we have double, we have increment. Now, let me combine those two functions to apply both to a number. So naturally, I'm going to call that double. So I'm going to have double, and then I'm going to increment it. So I'm going to multiply by 2 first, and then after I will add 1. So say double, then increment, something like that. And that's going, that takes x, of course, as an input, and that is going to, call for increment, and then is going to, let's just make like that, passing double for that x. Again, I apologize, guys. I don't know what's going on. I think it's the shades that I'm holding because the sun is really bothering me. So I really apologize. Again, with the double. So there we go. Now, if I want to use that double then increment, I can do. So you see what we have done, right? We have actually created double. That's a function on its own. Then increment, that's a function on its own. And then we have done this. We have taken increment and passed inside increment double x. So we're going to double first, and then after the result is going to be passed as a parameter or argument to that increment function. Right, so let's put this to test. Double, then increment, and let's say for instance 10, and we get 21. Why 21? Again, 10 multiplied by 2, that's 20, plus 1, that's 21. So it's the correct result, 21. Also, Haskell is statically typed. I personally love all the static typed programming languages. So in conventional programming languages, not functional, right? You need to define the type of the variable that you're declaring, right? You will say, for instance, const number or const a, and you will do type annotation, and you will define or decide the type that you want to give to that variable. However, in Haskell, it's intelligent enough to figure out on its own the type of the variable declared. So if I want to create a function, for example, I can say this is a function, and then I will do type annotation, that's an integer, and I need it to return an integer, right? In Haskell, you don't have to do that really. So I will change the name of that function. I will say that's auto inferred function. That's going to be x. Again, it's taking x and multiplying it by 3, for example. That's the cube. So you can do auto inferred function 10, and it's going to return 30, right? It didn't complain. It didn't ask you to define the type. The last great feature in Haskell is maintainability. So Haskell applications are modular, as we said. So they are composed of those small applications, small functions grouped together. It's like Lego. And therefore, it's very easy and cost-effective to maintain them, right? Because if there is an error, we will know exactly where the error lies. So if you have a program that is composed of 10 different applications, 10 different functions, if you will have an error, immediately it will point to that function. There is an error in that function. So you will go, you will, do the debugging. You will basically save your time and effort. Let me give you an example on maintainability. So lately I've been fond of temperatures. I don't know. I've created this, it was yesterday or maybe today. Oh, it was today, this morning, early in the morning. I've created this converter Celsius to Fahrenheit and Fahrenheit to Celsius in Node. So maybe I can take the same example actually and show you what I mean by maintainability here. So let's say, for instance, that we have a simple function that converts temperature from Celsius to Fahrenheit. So over time, you decide you also want to support conversions from Celsius to Kelvin. for example, we can define a function to convert Celsius to Fahrenheit. So initially I'm going to just give a name to that function, CTF, Celsius to Fahrenheit, and that takes C, which is going to be the Celsius degrees, and it's going to just C, it was multiplied by 9/5 plus 32, I think, if I'm not mistaken. Whatever, it's not the point. I think it was the input 9 divided by 5 plus 32. All right, so okay, not in scope. Okay, sorry, needed to do let, and maybe let's do CTF like that. That's going to be the name of the function. All right, didn't complain. Also, let me create a function that's going to take from Celsius to Kelvin. So we'll do CTK, and that also takes C, and that's going C plus 273. So we have CTF and CTK, both functions do conversions from Celsius to Fahrenheit and from Celsius to Kelvin. Now, if we'll do CTF 20, that's going to return us the result, 68. And if you'll do CTK 20, that's going to also return us the result. This approach highlights the Haskell's maintainability. How? It has shown me that how easy it is to add new functionality. So a new temperature scale conversion, for example. And that's without, risking or disrupting any existing functionality. So each function is self-contained and self-maintained as well. All right, so as I told you, in finance, in banking, you will never have any bugs. You will not have any unexpected behavior because you have an input, you have an output. As simple as that. You have independent applications, independent functions. All they are self-contained and self-maintained. Haskell, by the way, was created by mathematicians. So it's founded on mathematical solid ground, okay? That's why I love it, maybe. And you don't have to be a genius in mathematics. Even you don't have to be good in mathematics or love mathematics, because everything is going to make sense once you apply yourself. Why we hated mathematics at schools? Because we haven't applied anything. We had to know rules and, do the exams, or pass the exams and answer questions on the paper, but we didn't find any, any tangible result, or not tangible, but any real result. However, when you start create applications, even small applications, and you're going to apply the rules of functional programming, everything is going to be, to fall in place. Everything is going to make sense for you. Now, a simple hello world, we have seen it many times. I have one video about Haskell. I have other videos, but I haven't done the editing yet. But, a simple hello world, you will just create main. That's going to be a function naturally, and that's, we'll have here, like print in Python, or println exclamation mark in Rust, or console.log in JavaScript. We would do put strlen, and you will say hello world. Right, so that's hello world. So let's talk a little bit about the basic data models of Haskell. They are actually predefined or somehow decoded into the computer memory. So let's start by numbers, for example. So Haskell is, as we said, intelligent enough to decode some number as a number through the type interference. So you need not to mention the type, as we said. So you can do something like that. You can do addition, you can do multiplication, you can do division, right? And you can do subtraction. Okay, so you can do all of the basic mathematical operations. You can do, for instance, 100 plus, let's say, 23 multiplied by 43, whatever, minus 40. And you will have the result, 1049. Now let's move to characters. Like numbers, Haskell can, again, intelligently identify a character given in as an input to it. So we can do, for instance, A, that's going to, produce this output A. That's a character. If you want to specify the type, you can do colon T, and then you can do A. And that's going to give you that A is a character data type. If you'll say false, that's going to give you this output. It's a Boolean. False is Boolean data type. If you will do 23, if you'll do 23, that's going to be number. However, if you will do S, for example, without the double quotation, you will get an error. And the error says here that variable not in scope. There is an error. Why we have this error? Simply, Haskell compiler is just warning you that it's not able to recognize your input. So by this error message, Haskell is telling you that it's not able actually to recognize this input. If you will do S like that, that's fine. If you will do 2 like that, that's also fine, because you wrapped double quotes around a number. The same thing like a string, right? If you do like this, it's going to give you character. However, if you will do like this, it's going to tell you that this is a Boolean data type. And speaking of Booleans, it's pretty straightforward like any other programming language, basically. So if I will say true and true, it's going to give me true, that's truthy. If we'll do true and false, that's going to be falsy. If we'll do true or true, so this is or, right, in Haskell, that's going to be true. True or false, we're going also to get true. So be careful that true is capitalized, the T and the F. So if you will do true like that, it's going to tell you that perhaps you meant data constructor true, imported from Prelude. Now let's see lists, for example. List is like in any other programming language, actually, that's a list. So inside the list, you have to have homogeneous data types. You can do 1, 2, 3, that's okay. But you cannot do 1, 2, 3, and, frog, right? You can't do that. You'll have an error. You can also have lists within lists, but under the condition, again, that the data types should be homogeneous in all of the lists. So let's say that we have a list. The first list has 1, 2, 3. The second list has 4, 5, 6, and the third list has 7, 8, 9. Okay, so we have 3 different lists in one big list. And let's do number list, right? So number list in this case, it's not going already, it didn't give us any errors. So if you'll do number list, we will have those 3 lists in one big list called number list. And you can do the same with Booleans, with characters, with strings, with any data type. So we can also generate lists using mathematical expressions. So I'm talking about list comprehension. So let's say, for instance, that I have a list from 1 to 5, and I want to apply a square number on each number. So I want the square number of 1, the square number of 2, the square number of 3, and so on. So the way to do that in Haskell is you would do x multiplied by 2. So that's the square number of whatever the x is, whatever the input is going to be. Then you will separate that by a pipe, and that on that x as an input, you want to, iterate through that list of numbers and do this operation x multiplied by 2. So this is the way to do it in Haskell. So that's going to be from 1 to 5 or 6. Yeah, let's do 5. Okay, so there we go. 2, 4, 6, 8, 10. It took each number and it has actually multiplied by 2 and returned the result inside a list. So this is list comprehension. You can make it bigger, for example. You can make it bigger. Haskell is going to return the result without altering or changing anything. This is the power of functional programming. It's simple. You need to understand the function, how it works. It's clean. I find it very clean. I don't know. Let me know what you think, guys, in the comments below. But I find Haskell is a very clean language. If you would do the same, but without multiplying anything, that's going to return the same numbers from 1 to 100. In Haskell also you have tuples. So a tuple is basically a compound data type. It's just heterogeneous data types inside parentheses. That's all what it is. You can include numbers, you can include characters, strings, booleans, no problem. It's the opposite of lists, right? So if you'll say this is my list, maybe you can clear the terminal, right? So 2, 3, you can have string, you can have true, and no problem. You can print that, no problem. This is my tuple. All right, so it didn't complain. It just printed out what you have entered. Also, you can use both double strings or single strings if you want. Double quotation mark or single quotation mark, it doesn't matter. But yeah, if we'll do A, for example, right, no problem. It's going to print everything. If you do like this, just to prove you, again, it's going to print it, no problem. So yeah, guys, this was an introduction to coding in Haskell. I might continue, doing these videos about Haskell programming, and eventually we can create a full course on Haskell programming language if you want. If you like my content, please leave a like, share, or do what you do. I don't know. Thank you so much for watching. Thank you so much, dear members, for supporting. And yeah, with that, I will see you in the next video. Till then, stay safe and be well. Take it easy, guys. So constructs in Haskell and in any other programming language are very useful. As Haskell is a purely functional programming language, it should use some methods or tools to help the language to manage data and control flow. So that's all what it is. The pattern matching, the guards, the where clause, the recursion, the higher order functions, and Lambda expressions are exactly needed in Haskell to manage data, whatever the data is, primitive or compound, and whatever the control flow is, right? And control flow, we know it's a combination between conditionals and loops. But as we don't have if-else statements in Haskell, and also as we don't have loops in Haskell, so that's going to be substituted by pattern matching / guards and recursion. And I'm going to show you the difference. And I think you're going to love guards more than pattern matching, but just I don't want to force or just to bury you under my beliefs. But any other developer, especially those who come from other programming language backgrounds like Python, JavaScript, Ruby, whatever, they fall in love with guards directly because it's very expressive and concise at the same time. Everything in the syntax of guards makes sense. Also in pattern matching, I have nothing against pattern matching. So let me actually create different folders. L1, that's going to be lesson 1 and lesson 2, lesson 3, 4. If we're going to leave it because the higher order functions I'm going to show you directly in the interpreter, we're not going to compile anything. And we'll go to 6, the Lambda Expressions. And don't worry, you're going to find the GitHub repo for all of the code, so later you can copy that and practice with it and changing the code if you want, do what you want. So even if you're not practicing with me right now, if you don't have Haskell installed or anything that it's preventing you from coding, later you can do that, no problem. And again, you're going to find a video, just a card above appearing, you can click it and it will take you to another video. Just actually the first video in Haskell on the channel is going to show you actually how to install Haskell on your machine. And I'm using Windows Subsystem for Linux too, by the way. That's Ubuntu interface, and I'm using Fish Shell, the friendly interactive shell. This is the bash, that's the normal bash, and this is the fish. Okay, so let's go to L1 folder and let's create pattern matching.haskell file. All right, so what is pattern matching? Pattern matching is a technique that you can use as a developer to deconstruct data structures and match specific forms of data. Let me give you an example. Let's say, for instance, that you have a list of different types of coffee, right? The different types of coffee, you want to have a description for this. So for instance, if you want to type espresso, you want to find a description for espresso. If you want to choose latte, you will find a description for latte, and so on. I'm going to try not to, give you the typical examples in other tutorials, like factorial numbers. Well, maybe factorial I will show you, but maybe the Fibonacci sequence, the polynomials, and all of that, I will try not to. I will try to make it lighter. Right? Maybe I can just type here pattern matching to know what we're talking about. So let me create a function. I'm going to call it coffee type. This function actually is going to take a string and it's going to return a string. Now I can take that function and I will pass to it the string, and that's going to be the description, right? I'm matching the description to the coffee type. So we'll say here strong, for example, and bold, right? And actually, let me just copy this. Let's yank this and let's paste 2 times. And let's have the 3rd time for the unknown type, right? So let's also say here latte, for example. I'm not sure if lattes were written, maybe 1E. And here we'll say milky. Sorry guys, but I hate latte. Milky and weird. Also for cappuccino, frothy and rich. Now, if we have any other type, if you will pass anything else, that means that we have an unidentified coffee type or unknown coffee type. So the way to do that is with this underscore. So coffee type with this underscore, that means that that's going to be any other coffee type, unknown coffee type. Tell me, this looks to you like if-else statement, right? If you have espresso, print strong and bold. Elif or else if latte, print this. Else if cappuccino, print this. Else, print this, which means otherwise, or in any other cases, print unknown coffee type, right? That looks like if-else statement. Okay, now let's create the main function, and be careful, you need 2 spaces, 1, 2. If you'll do tabs, you're going to get an error, I'm telling you. Now let's do put stir line, and we'll say here your coffee description is whatever. And simply we're going to print that. So print coffee type, and we're going to pass, for instance, espresso. Let's make it latte. And let's put here anything. Let's put here bread. All right, so let's go and save that. Let's use the compiler to compile our file. What was it called? PM. Okay, PM, GHCI, PM, Haskell. Okay, linking, no errors, awesome. Let me show you what we have. We have now the executable, this PM without extension. That's the executable file that you want to run. the Haskell interactive, the Haskell file, and the output. We don't care about those. So you want to run your executable, and you will have here your coffee description is, and you have strong and bold, milky and weird, and you have the last type of coffee, which is unknown coffee type. So this is pattern matching in Haskell simply. Now the guards are written this way. First of all, the guards actually provide a way to test conditions in function definitions. That's, as I told you, that the developers love guards, especially those who come from different imperative backgrounds, imperative programming language backgrounds. They love it because it's very expressive, very concise, and very effective in the same way. And it's very beautiful to look at. Let me show you. Let me create a function. This function is going to just categorize the books based on the number of pages of each book. So if you will have a big book, more than 500 pages, that's going to be, for instance, a novel, a big novel. Less than 100 is going to be novella, for example. Less than 200, short story, and so on. So let me call it book category. And this book category function takes an integer and returns a string, right? Now, the guard clause, so that's a clause, by the way, right? The guard clause is used for different page ranges. So in order to apply our function, we will use the book category for different amounts of pages, right? So that's going to be whatever. The pages here is symbolized by integer. So you need to enter the number of pages as an integer, and you will get a result as a string, which is the classification of the book. So book category pages and that pipe. Now we're going to check out if the pages are less than 100 page. In this case, that's going to be a short story, right? We need to do spaces all the way. I know it's a pain in the butt, but Haskell is very picky when it comes to spaces versus tabs. So if pages is less than 300, that means that our book is a novel, right? Let's get back all the way to the beginning of the line and push with spaces. I'm pretty sure there is some sort of extension, something that helps, making auto indent or, to reduce the time in those silly things. I prefer to go with you just simple Haskell code programming, with no frameworks. I hate frameworks, guys. Okay. You need to know that. I'm saying it up front. If you know me or if you follow me on Twitter, you know my clear opinions about that and my discussions with a lot of friends about frameworks. And you need to know programming. You need to learn programming, not a framework, even not a language, right? You need to know the how computer thinks. I'm not telling you to go and learn machine code, but at least you need to learn C. You need to have a good idea about assembly language and how C compiles the assembly and how assembly compiles the machine code, right? This is programming. This is computer science. Frameworks it's all about settings and configurations and all that sort of thing, which I personally hate. I don't like. I find that I find a lot of people fall for, especially the newbies. I don't mean to disrespect, of course. Newbies, I mean our junior friends who just started to learn coding. They fall for this. They go and start learn frameworks, and they get hyped too much about Express and Django, Flask, Laravel, all of that. Wrong. You need to learn a language, a programming language, the logic, how computer thinks. If you understand data structures, that's how a programmer, or at least any software engineer, would tell you that you need to learn data structures. You don't have to worry a lot about bugs or syntax. Syntax is byproduct, That at least this is my philosophy. Syntax is my byproduct. It's not important. Even typing code blindly, it's not impressive. What's impressive really is to structure your code in a good way that anyone else can read your code without any comment and understand immediately what you want to say. This is engineering. This is software engineering. And believe me, I know it the hard way. I fell for a lot of mistakes. I'm just giving you my experience to not fall for the mistake. Learn the language, forget about the extensions, forget about the frameworks, just concentrate, focus on the language, learn it, go deeper, code a lot, practice a lot, practice. Just you can type things and understand what you're typing without copying, This is programming. I got carried away when I talk about this because this issue is very sensitive, especially on Twitter. I see a lot of my friends who, have different opinions, and a lot of them, they share my opinion. But yeah, that's tip for you, my friend. All right, so if pages are less than 500, or let's make it 1,000, that's going to be a Stephen King book, for example. Oops. Right? Now, you want to say else here, right? Otherwise, or else, that's a plug. Otherwise, if it's, more than 1,000, for example, that's going to be otherwise. So otherwise, we can say that we don't know. Now let's go to our main entry. So main equal to do. 2 spaces. Again, I'm repeating 2 spaces. Spaces in general, but just don't do tab, right? You will get an error, believe me. So 2 spaces, and we can do put stir line, and you can say the category of your book is, then we're going to print, and I'm taking the book category, and I'm passing now the number of pages. That's why when we have structured our function, it takes an integer. That's going to be the number, let's say 350. And it's going to return to you a string. And that's exactly like conditions, right? That's exactly like conditions in any other programming language. All right, so let's go and do like this. Okay, compiled successfully, awesome. And let's run guards. And now we have the category of your book is Stephen King book. Let's see if we will do, for instance, of course, if you will pass anything, right, it's not going to compile because variable not in scope. Integer, that's not an integer. It's telling you, hey, it's yelling at you, telling you, hey, that's not an integer, man. I need an integer. So what are you doing? So we need to fix that. But if I will do, for instance, 10,000 pages or 100,000, doesn't matter. Compile, all right, and let's run that. And we got here, we don't know, because that's over what we have defined here, over 1,000. If you, even if you will do 1,001, you're going to get the same result, right? We don't know because it's more than 1,000. All right, so this is guards in Haskell, guys. It's very intuitive, very beautiful to write, and I'm pretty sure you will use it. By the way, after we're going to finish this series, so this is the 3rd video in the series, I hope that we will have the time to create some applications together, like video games, simple video games, nothing excessive, simple video games, simple applications, like weather application, like banking system application, stuff like that. You will get the chance to practice more, because all what you know now is just theoretical, or not theoretical, but just you're seeing examples with me. But once you will practice this in useful applications that you can actually code yourself, believe me, you're going, first of all, to be very proud of yourself. And the second thing is that these concepts are going to be cemented in your brain. You will not forget it. The where clause is an awesome construct. The where clause reminds me directly of SQL code, right? If you've coded in MySQL, PostgreSQL, SQL Alchemy, SQLite, whatever, you have this where clause where you're just selecting or we're just specifying. The difference here is we're not going to retrieve anything from a database table, but we're going to determine the thing that we want to determine. So in short, the where clause is very useful for you as a programmer for breaking down a very complex expression to make it simpler, right? It's breaking it down. If we have this function called population density or pop density that takes two floats and returns also a float. If I will take the pop density and I want to pass inside, we need two floats, right? So population, let's say for instance, so we need two floats. So that's going to be the population and the area. That's the density of the population is by taking the population and dividing it by the area. So you want to say pop density in arguments population and area is equal to density, where the density is equal to the population divided by the area. Just make it like that. You see how it works? So you created this function, you defined this function, and you passed inside the population and area, which should be float numbers, and you want to return a float as well. This is going to be the density. This density is calculated as follows. Population, go to your main entry point for your application and just pass here the pop density function and pass whatever the numbers you are. It should be whatever, should be anything, but they should be floats, right? So for instance, in Egypt we are 110 million 0.25 whatever, and the area is, I don't know, I really don't know and I don't care, 85.25 as well, right? Or just let's make it 78. Again, this is the where clause, and the where clause is defining the density that's going to be the population divided by area, and that's going to be ultimately the density that's going to be returned in a form of float. Now let me show you if we will compile that where, right? You see that we have our calculation. Now let's see recursion together. Now recursion simply is, just let me write here, recursion. I've explained 4 years ago functional programming in general without taking a specific language, and I've talked about towers of Hanoi. And I invite you to take a look to this beautiful video by Computerphile. This professor is going to explain to you what recursion actually is in Python. It's going to use Jupyter. So yeah, recursion doesn't only exist in Haskell, but also in other programming languages like Python. Now, let me explain to you recursion very easily. Recursion means that when a function calls itself, 3 words. That means that you pass the function as an input inside the function itself. So it's going to be called from within itself. And the best example, of course, is factorial. Now, factorials are the best example for recursion because we need to do the same thing over and over and over again. So we will have a base case. So the base case is going to be 0. And if you want to get the factorial of 5, that means that you want to multiply 5 by 4, by 3, by 2, by 1, until it just reaches the 0. So that's basically the 1. Well, factorial of 1 is 1, right? The base formula for that is going to be if the factorial of n, that's the number that you're going to pass, you want the n to be multiplied by the factorial of the n minus 1. That's the basic thing you're looking for. That's in general, that's mathematics, that's not programming. Right, so let's try to see how recursion works in this case, because if, let's say, I want to pass 10, for example, I want to find the factorial number of 10, that's going to be a high number. Imagine that factorial of 5 is 720, if I'm not mistaken. That's 720. So let's say if you want to pass 100, that's going to be recursive 100 times, from multiplying 100 by 99 by 98 all the way till 1. That's really a lot, and I believe you will have a Stack Overflow. It will be out of bound. So let's see how we can actually create that. Let's say that our function is called factorial, and that takes an integer and returns also an integer. Okay, that's not a comment. If I want the factorial here to give it a base case, that's going to be 1. That means that the factorial of 0 is actually equal to number 1. So if I want to do this recursive case, so that's the base case. So this is base case, and this is the factorial, or the recursive case, right? Recursive case. Here I'm going to take my factorial function, and I'm going to pass the n, and that's going to be equal to n, the same exact thing that just we have written above, and that's n minus 1. Now in the main function, that's going to be with 2 spaces here, and let's pass factorial 5, for instance. Let's just make like that. We have an error. Oh, I need to print it. I apologize for that, guys. Okay. Just clear the terminal. Okay, no errors. Awesome. And now, if you will do recursion, you should get 120, not 720. I apologize. Yeah. Okay, so that's 5 multiplied by 4, by 3, by 2, by 1. Right, that's 120, not 720. Right, so this is simply recursion. It's a function that calls itself until some sort of condition is met. In this case, when there is nothing left in the recursive sequence. Let me show you if I want to change the 5 by 50. That's going to be a lot. I don't believe that it's not going to run. Okay, that's a negative number, right? And you can see it's huge. So that was it, guys. Recursion means a function that calls itself within itself. Let me show you if we'll have a crazy number here. Let's have, for instance, let's have whatever. Of course, nothing will happen. Look, 0. Why 0? Because it can't calculate. It cannot. The memory doesn't allow that. So higher order functions, what are they, right? Higher order functions. Simply, higher order functions are treated as any other object. You can pass these functions to any other function, and you can expect to have an appropriate result. Let's go ahead and see what we have from higher order functions. For that, I'm going to open the interpreter, right? Just to show you directly, just increase the font. The first one is map. The map function is a function that can apply a different function that you can create to a certain data type, right? So let me show you by an example so you will understand better. So let's say that I want to create a function. I'm going to call it increment. That's going to take whatever the number that you're passing to it, and it's going to increment it by 1. So that takes x as an argument and returns x plus 1. Now, if you will do increment 2, you're going to get 3. If you'll do increment 3, you're going to get 4. If you'll get 4, you're going to get 5, right? That's a simple function. Now, you can map that actually and pass the increment function to that map function, right? And you can pass a list. And when you will hit enter, you will have 2, 3, 4, because it has iterated through that list of 1, 2, 3 and incremented each number by 1. And I find this awesome, to be honest. I find this map function to be awesome. It maps, right, whatever the function to whatever the data in your data type. So in that case, a list, for example, because it's an iterable data type. So this is map simply. Again, these are small examples that are aiming to explain to you the idea, but of course in bigger programs you can use map in more complicated way. Another function I want to show you is filter. So filter simply selects elements of a list that satisfies a certain criteria or predicate. So it's basically a function that returns a Boolean value, whether true or false. Again, let me give you an example. Let's create a function that's called isEven. And this function simply is going to check out if the number you're passing to it after the division by 2 is equal to 0, means the modulo or the remainder of the division is equal to 0, that means that it's an even number, right? So 2 divided by 2 is equal to 1, with no remainder, no fraction. Otherwise, it's going to give you false. Otherwise, it's going to be an odd number, right? So it's going to be a false. So simply it's going to take a number and it's going to check out if that number, so in Python, for example, you would do modulo, right, with the ampersand. In Haskell, you would do with the backticks mod and closed backticks. And that's going to take 2 or divided by 2, and the remainder should be 0 in case of an even number. Now you can take the filter function and pass to it the isEven function that we just created, right? And that should be in the form of list, by the way. So if you want to check out any number, if you will do like this, you will have an error, right? Because you need the list. So if you will pass numbers 1, 2, 3, 4, 5 in a list, you will have only 2 and 4, which means 2 and 4 are true, are Boolean values. They return Boolean values. And of course, the 3, 5, and 1 are not true. Okay? If you will pass 5 only, you will get an empty list, which means nothing. That means that 5 is odd. If you're going to pass 2, you're going to get 2. If you will pass 2 and 4, you're going to get 2 and 4. Right? You'll pass 0 and 1, you will get 0. Similarly, you can do with isOdd. So you can do isOdd, and that's again taking a number, and this number is checking out the remainder of the division of 2 that should be equal to 1. Now, if you will filter out, that's what the filter words comes from. It sifts through the list and brings you whatever is based on your condition, is odd, is even, or whatever. So we're going to pass isOdd, and again, I'm going to pass a list. So we'll say 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, right? So of course, we'll have a filtered list of the odd numbers only, 1, 3, 5, 7, and 9. This is another higher order function. We have, for instance, fold L. That's going to take numbers from the left and it's going to do whatever operation you want to do to the right. So it's going to do from the left to the right. So if you will pass a list, for example, of different numbers, it's going to add the numbers if you want to add. Of course, you can do subtraction, multiplication, division, or whatever, but it takes from the left to the right. So to do that, you will just specify the type of operation you want, and you want to start from 0. Then you want to give a list of numbers. So it's going to add numbers from the left to the right on the basis of 0. So it's going to start 0, 1, 2, 3, 4, 5, and so on. and that's going to give you 15. 1 plus 2 plus 3 plus 4 plus 5. There is also another higher order function called fold R, and that does the same thing but from the right to the left. So let's try it on multiplication, for example, and that's going to be 1, not 0. That's going to start from 1, right? Because from the right side, you can't have 0 from the right. And let's say also 1, 2, 3, 4, 5, right? You're gonna have 120, right? So 5 multiplied by 4, by 3, by 2, by 1. That's exactly the same thing when we have done factorial of 5, which resulted in 120. That's 5 multiplied by 4, by 3, by 2, by 1, decrementally. Right, let's see what else we have. We have another higher order function called sort. So sort sorts basically the elements of a list. So if you will pass numbers in a list in an unordered way, sort is actually going to sort the list, right? It's going to order the numbers in that list in an ascending way. But for that, I will need to import from data.list, and I will need to import that sort function. Right. So what we can do is we can sort different numbers in the list. I'm going to type crazy numbers now. Right, and the last one, doesn't matter. Oops. And let's close the list and take a look at that. It has ordered all of the numbers from the smallest to the biggest. So indeed, this is an awesome function. We have another function called zipWidth, like that. So zipWidth actually can add different numbers from different lists. So if you have a list with 1 and 2 and another one with 3 and 4, it's going to add 1 plus 3 and 2 plus 4 and return them in a list. Let me show you if I want to add numbers. So again, you need to specify that you're adding, and you have a list here from 1, 2, and 3, and another list for 4, 5, and 6. You're gonna get another list with the addition numbers. 1 plus 4 equal 5, 2 plus 5 equal to 7. So 1 plus 4, 5, 2 plus 5, 7, 3 plus 6 is 9. So you can see that this is the result of addition of the numbers by order. So 1 plus 4, 2 plus 5, 3 plus 6. You can do the same thing with negative, for example. You're gonna get minus 3, minus 3, minus 3. Now let's say, let me just do like that. Now let's say, for instance, that we have another number, 9, for example, that's going to be totally ignored. If you have more than number, not only a number, an additional number, but different additional numbers, again, it's going to ignore them. Zipwidth matches exactly by positions, by indexing. 0 index, first index, second index, and so on. That's going to work if I'm going to also match numbers here. Aha, now it's different. Now Haskell understood that for this key, for this value, I have a corresponding value that I need to add with. So this is zipwidth. It takes the addition or whatever the operation you want to do between two lists and unzip them as a result. The next higher order function we have is called takewhile. Takewhile is an awesome one. Takewhile basically takes elements from a list while a certain condition is true. The next higher order function we have is called takewhile. Takewhile is an awesome one. Takewhile basically takes elements from a list while a certain condition is true. For example, if you have a list from 1 to 5 and you want to take all of the elements in that list that are less than 3, for example. So let's see how we can do that. We can say takewhile and less than 3 in this list 1, 2, 3, 4, 5. And of course, we'll get a list of 1 and 2 because they are less than 3. If you will do less than or equal to 3, you will get 1, 2, and 3, right? If, I don't know, you will do 1, you will have an empty list because there is nothing less than 1 in the list. Of course, if you will do equal to or less than 2, you will have 1 and 2, right? So this is take while. The opposite of take while is drop while. So if this function returns elements based on certain conditions, the drop while deletes numbers based on certain conditions. So if we'll do drop while, and we'll do like this, 3, also the same example to be clear to you guys, you will have 3, 4, and 5. That's exactly the opposite of 1 and 2. So take while has returned the numbers based on the condition. Drop while has deleted or dropped down the numbers based on that condition and returned the remaining here. Right? That's going to be the exact same thing if you would do like that. You'll have only 4 and 5. Right? So let's make like that. It's going to be 4 and 5 because we have dropped 1, 2, and 3, because all of the numbers equal to or less than 3, we want to drop them. We have 2 more awesome ones, all and any. 2 brothers, all and any, or brother and sister, all and any. So all actually checks if all elements in the list satisfies a predicate or a certain condition. So what you want to do is you want to take all and check out if the list that has those numbers are even or not. Of course, it's false. But if we will delete the odd numbers and pass only, I forgot the one. If we'll only pass an even list, that's going to be true, right? So this is all. Everything in the list should be even. The opposite is his sister, Annie. So if all is very uptight, Annie is more tolerant. So Annie is going to check if any number in the list has an even number. Of course, it's true because we have 2 and 4, which are even numbers. And that's also going to be true because we will have 1, 3, and 5, which are odd numbers. The last thing that I want to show you is the Lambda functions. So Lambda function is a simple anonymous function that doesn't have a name, that you can use it just to return something simple if you don't want to write a lot of code. The symbol to write a Lambda function is this one, just a backward slash. An anonymous function or a Lambda expression that returns the temperature in Fahrenheit. So it's going to convert numbers from degree Celsius to Fahrenheit. And that's going to be the degree Celsius, right? That's the input. And I want to return the degree Celsius that's going to be multiplied by 9 divided by 5. Add to it 32. Now I want to print all of that and I want to pass now the number, the degree Celsius that we want to convert to Fahrenheit. That's our argument. Let's run that, compile, Lambda Haskell, compiling. All right, awesome. And let's run our Lambda expression and we have 77.0. You can do that as well in the interpreter if you prefer. So you can print with the backward slash C that takes C and returns the degree Celsius multiplied by 9 over 5 plus 32. Right? And also we can pass to it 25, and here don't forget that we need another parenthesis, and that's going to give you the same result, 77.0. So you can compile it or you can run in the interpreter. That's going to work fine. All right, so these were our higher order functions in Haskell. We have explained pattern matching, we have explained guards, we explained where clause, we have seen recursion, we have seen higher order functions, and we have seen Lambda expressions. Thank you so much guys for watching, and I will see you in the next video. In today's lesson, I'm going to teach you more functions that can be easily used in Haskell without actually importing any type class. So the first function that I want to show you is called head. Now, the head function works on a list. It returns actually the first of the input argument, which is basically a list. So let's say that we have a list of 10 values or 10 numbers. We are generating the first element of that list using the head function. Let me actually create that list, x equal to 1, or let's do it like that, dot 10. That means this is a list from 1 to 10. Enter. Now, if you will type x, that will show you that this is indeed a list from 1 to 10. Now, the way to use that function is you will print head of x. And that will print number 1 because this is the head of the list. So this is head, simply a function that returns the first value in a list. The opposite of head is tail. So you have this tail function, which basically takes a list as an input and yields the entire list without the head part. So if you will print tail x, that should return from 2 to 10. You have also a function called last. Now, as the name suggests, it's going to yield the last element of the list that is provided as the input. So again, on our example, the x list from 1 to 10, if you will print last x, that's going to print the last element of that list. Also, you have a function called init. Now, init works exactly as the opposite of the tail, right? It takes a list as an argument and will return the entire list without the last entry. So let's go ahead and check that out. If you will print init x, that's going to print from 1 to 9, excluding the last element. We have also a function called null. Now, null is a Boolean check function that works on a string and returns true only when the given list is empty. So let's check that out. If we'll do print null x, that should be false. Now let's create a y list. This is an empty list, right? And if you will do print null y, that's going to be true because, the y list is empty. So this is null. It's a Boolean check function, checks if the list is empty or full. There is also the reverse function. So the reverse function is a very interesting one, really. The reverse function works on an input, and to be precise, it works on a string input. Then it converts the whole input into reverse order and then give the output as a result. So let me create a new list. I'm going to call it fruits. So this is a list of different fruits, right? So let's say orange. So this is the fruits list, orange, banana, apple. Now, if you will print reverse fruits, that should get me apple, banana, orange. It has just printed the list backwards. The same exact thing you can do on numbers, right? You can do reverse x. That's going to be from 10 to 1. Also, you have a function called length. Now, length is a function that is used to calculate the length of a list given as an argument. So if you have a certain list in your program and if you want to know the length of that list, you can use the length function. So of course you can expect that the length of the x list is going to be 10 and the length of fruits list, that's going to be 3. Now take is a very interesting one. Take actually is used to create a substring from another string. So let's say, for instance, that you have a very big list from 1 to infinity. And this is a concept that we have discussed in earlier lessons about laziness and how Haskell is a lazy programming language. And indeed, it's a very memory efficient feature. So if you have this list from 1 to infinity, that's going to take a huge amount of bytes in your memory. Take actually takes what you want from that infinite list. So this infinite list is not stored in the memory, but whenever you want any numbers from that list, take function is going to extract those numbers and print them out to you. So of course our x list is from 1 to 10. So if you will say print, then here take 5 numbers from that x, that's going to be from 1 to 5, right? We can if we'll do let infinite, or just inf num equal to a list from 1 dot dot means to infinity. Again, if you will do print take, let's say 20, which means take please 20 numbers of that infinite list. So we're going to pass that list inside here, and it's going to print from 1 to 20. Also, there is the opposite of the take function, which is drop. Drop is going to delete numbers. The number that you're going to precise in your function from 2, that's going to be dropped from the list. So if you will do print drop, and let's say we want to drop 6 from our X list. So from X, and that's going to give us from 7 to 10. The function actually has dropped from 1 to 6. You have also other functions like maximum and minimum, maximum returning the maximum number and minimum returning the least or the minimum number in that list. So let's have a new list. Let's call it bnum, or big numbers. And that's going to be a list of, let's improvise 1, 2, 3. So I want to take the maximum number in that bnum list and the minimum number. So let's say that you want to print the maximum number of that bnum list, right? So bnum 7854. That's the highest number in that list. Similarly for the minimum, you can expect the opposite for the minimum, right? That's going to be 0. Also, you have other functions like sum. So that's going to add all of the numbers in your list. So again, if we'll apply that on our X list, we can do print sum X. That's going to, add 1 plus 2 plus 3 and so on, and gives us a result of 55. Also, there is the product function. The product function is going to do the multiplication of all of the numbers inside your list. So let's try to do that. Print product X, and of course it has multiplied all of the numbers. The last function we have today is lm function. This function is very nice actually. It's going to check whether a certain element exists in the list or not. So you can think of it as a search function. Let's say for instance that in our lists bnum, so simply you're going to do print lm passing the number, which is 147 in that list, right? So in the X list, and that's going to be false. And I've passed, of course, the wrong name of the list. That should be bnum, and this is indeed true, right? Because 147 indeed exists in the bnum list. And if you'll do any other number, for instance, anything, that's going to be false. So in mathematics, composition, for example, is denoted by f, curly brace g, and passing inside the argument and closing the curly brace. So the g here is a function, and its output is going to be used as an input of another function, which is the f. So maybe I can show you a final example on a function composition. Let me create a function called foo_even, right? This foo_even is going to take an integer and is going to return a boolean. Another function, I'm going to call it foo_not_even, and that's going to take a boolean value and is going to return a string. Now that boolean value is going to be an input inside that foo_not_even function to return a string. So I'm going to take the foo_even function, I'm going to pass x, if x the remainder of the division by 2 equal to 0. We're going to check if the remainder of the division of that number by 2 is equal to 0. That means that this is an even number. Then I'll passing here 1, 2. Do not forget about the indentation. Then true. Else, that should be here, false. Then I will take the foo_not_even x if x is equal to true. In this case, I want to, two spaces, then I will say this is an even number. Else, this is an odd number. Mean do two spaces, and I'm doing a put stir line. We'll say here example of Haskell function composition Then finally, we're going to print. So we're going to take the foo not even dot foo even, right? So we have actually accessed the foo even from within the foo not even function. And I'm going to pass, of course, the number that I want, which is 15, for instance. So this is an example of function composition in Haskell. Now let's go ahead and try to run that program. So let's go ahead and compile that. Compiling, okay, good. And then let's run that. Let's see what we have. And again, guys, after the compilation, I always like to repeat those words in order to be cemented in your head. After the compilation in Haskell, always you have 4 different files: the Haskell interface, the Haskell file, the output, and the executable, right? So what you're interested in actually is that one, the executable, right? So let's run that. And we have here example of Haskell function composition. This is an odd number, right? Because it's 15. If you will change the number, let's change that number to, let's say, 4. Compile that again, and let's run that again. This is an even number. So yeah, guys, that's it for this lesson. We have studied the higher order functions. We have studied the function composition. We have talked a lot about functions in this video and the last video, and that's absolutely fine because we're actually studying a functional programming language. So you can expect that we will talk about functions all the time. In the next lesson, we're going to study modules in Haskell. Thank you, and I will see you in the next lesson. Hey, what's going on, everyone? This is Backbrace channel. My name is Amir, and in this video we are going to continue our Haskell series. Today we're going to talk about modules. So far we have studied many things in Haskell. We have studied how to set up the environment, the basic data models, basic operators, decision-making, types and type class, functions, higher order functions, function composition, and today is the modules turn. And let me create a folder. I'm going to call it lesson 4. So let's talk a little bit about modules, what modules actually are. So if you have coded in Python, for example, you know that you have modules, right? Modules are simply a code that someone else wrote it. It's full of functions, classes, types, you know, stuff like that, that you can actually utilize in your own code, right? So you have, for instance, a time module, you have calendar module, right? You have different modules. There are modules that you can install and modules already embedded in the system. So you have third-party modules, and you have modules that already pre-built in the system. In JavaScript also you have ES6 modules. In Java, for instance, you have packages. So the first module we have is the list module. And the list module is used with the list type data. Okay, so once you import the list module, you have a wide range of functions at your disposal. Let's go ahead and take a look what list module is actually. Module 1. Okay, that makes more sense. So we will import data.list. This way you have actually imported the list in your Haskell code. The same exact thing, you can do it in the GHCI. You can do import data.list, and immediately it will change the prelude and you're inside data list. You can utilize actually all of the functions available in the list module. So let me just exit that. Let's get back to our file and let me create the main entry point. So the first function that I want to show you in the list is a function called intersperse. So intersperse actually will separate one string and will separate the characters of the string by whatever the separator that you're going to choose. So let's say, for instance, that I want to use the intersperse method, and the separator here is going to be dot. It could be that pipe, it could be forward slash, could be anything. But just let's make it the pipe and the word or the string that I want. So let's say I love Haskell. Okay. So that's the first method. The second method that I want to show you is a method called interselate. Forgive me if I'm mispronouncing that, but I think it's pronounced intersalate. And intersalate, if you have, for instance, a list and you have different elements in that list, you're going to insert a space, for instance, and that space is going to move all of the commas between those elements in that list. So you can have different words in a list, and they are separated by commas, of course, and the intersalate will remove the commas and substitute that by spaces and will form you a whole sentence. So let's actually try that out. Intersalate, and we have a white space and a list. This list, let's say for instance, Haskell is great. Okay, so these are 3 words in a list. Another method is called split at. So if you have, for instance, a string, this string you want to separate from a certain index. So it's based on the 0 index. So index 0, that's the first letter, index 1, that's the second letter, and so on and so on. So you want to come on one specific index and you will separate. So let's say that we have the word apple. If you want to separate like that, you will come on index 3 because that's operating from index 0, index 1, index 2, and on index 3 you will separate. Okay, so that's the idea. The method is called split at. So let's try that out. Split at, and we're going to split at index 3, 3 as we said, and the word, let's keep it apple. The last method that I want to show you, we have seen it before, is the sort method, where you have a list of different numbers. They are not organized, of course, they are unordered, and you want to use this sort method in order to order the numbers in an ascending way. So let's do print sort, and we'll have a list of, crazy numbers. So let's do like that. And that's enough. Okay. Right, so let's go ahead and compile that. Let's do GHC, and that's m1.hs output and m1. All right, and let's run m1, and there we go. We have here I love Haskell. Each letter is separated by a pipe. That's the intersperse. The intersalate is the next one, where we had a list of 3 different words. Haskell is great, and from that list we have produced a string. Haskell is great. Also, we have the split at method, where we have actually split in a certain index, and we have created this tuple, just composed from 2 different words, app and le. The last one, which is the sort method, it has actually sorted all of the numbers from 1 all the way to 6,781. All right, so that's basically the list module and some of the methods embedded in that list module. The next module we have is the char module. Now, the char module has plenty of course, predefined functions to work with the character type. So let me actually show you in a file. Let's call it m2. We're going to see only 2 methods, right? So the first one is, so first of all, of course, as always, we need to import that. So I'm going to import data.char. So actually, I'm going to show you 3 different methods in the char module. The first one is toUpper. This function, as its name describes, it changes the character from a small letter to a capital letter. And let's do print. The method is called toUpper, right? So toUpper with the U capitalized like that. And the character simply, we can make it A, for example, right? We have also the opposite, toLower. So that's toLower, and let's make it B, for instance. So these are the 2 main methods in the character module that converts the letters from small to capital and from capital to small. So let's do GHC m2.Haskell O and m2. All right, so you can see here that it has converted from small a to capital A and from capital B to small b. Let me actually show you another one. Now the words method is going to take a whole string, a whole phrase, and it's going to, put each word in that phrase inside the list separated by commas. So the method is called words, and you can here have a string. So you can say Haskell and Rust are not friends. Right. So let's take a look what this will do. Compiling, let's run that. And you can see here, oops, let's just make like this. You can see here that it took the whole string and it has separated it by commas and put it in a list. Now the third module that we have is the map module. So the map is an unsorted value-added pair type data type, and it's very widely used module with many useful functions. So let me actually give you an example to understand better. And of course, the first thing you need to do always is to import data.map, and we're going to do map like that. So here what I have done actually is that I have imported the map type from the data.map. That's the map type. I need that because I'm going to define a function, and this function is going to take an integer and will return a map. So that's why I will need this map type here. And if you're going to run that on the GHCI, you're going to need to import this way. Import qualified data.map as map. And I'm going to call this function myMap, right? That's going to take an integer and return a map. Integer, because that's going to be the pair. Because what I want to do actually is going to map each number to its corresponding number. So if we have 1, that's going to be 1 corresponding to 1, 2 corresponding to 2, 3 corresponding to 3, and so on. So that's actually a mapping function. You're mapping numbers. That's the thunderstorm here in Poland. Okay, so I want now to create a map from a list of pairs. So I'm going to take the myMap function that's taking n as an input, and this is equal to map.method called fromList. So from list here, and inside here I'm going to map make pair, right? That's another method. I'm going to say from 1 to the n number. That's not all, because I need the where clause. So where, and here I want to define this make pair helper function to create pairs of, the number and its corresponding number. The x and x inside this one, basically. Here, for instance, you have x, the integer, and x inside the square brackets. So you have, as I told you, 1, 2, 3, and so on. Right? I don't want to repeat myself, but yeah, sometimes repeating is good. So make pair x is equal to x and x in square brackets. Main equal to print, and we're going to take the myMap, not make pair, myMap function, and you can say 4, for instance, right? So you're going to have pairs 1, 1, 2, 2, 3, 3, 4, 4. Let's go ahead and compile that. Okay, that's 4. That's actually 3. Yep, and that's 3. Okay, so let's try something out. Let's go down here and let's do main input output. Okay, still. All right, sorry for that, guys. So we have here, so I think we need to, okay, so that's also going to work on the compiler. So as per my understanding that this only works in the interpreter, but turned out that it works also for the compiler. So let's try that out. Oh, okay. So sorry for that, guys. So this qualified here, this actually works also for the compiler. Import qualified data.map as map. Does that mean that if I will delete this, it will still work? Let's try to compile that. Okay. So we need both, actually. We need both. We need to import data.map and also import qualified data.map as map. Okay, linking, awesome. Okay, so let's try that out, M3. And you can see here that we have from list, we have 1 pair to 1, 2 pair to 2, 3 to 3, 4 to 4. Now let's go ahead and see the fourth module, m4.haskell, and that's going to be the set module. So the set module actually has a lot of very useful functions to manipulate mathematical data. So the set is used for math. So let's import first. Import qualified data.set as set. If I will have text1 and we'll say here, hey Jude, and and let's have t2, and we'll say here, for instance, smooth criminal, and we'll set or we'll define set1 equal to set dot from list the t1, and exactly the same thing for set2 equal to set dot from list t2, then print set1 and set2. All right, let's do m4. Right, and you will find that we have used this method from list, the same one that we have used in the map module, right? From list, what it actually did, it has deleted all of the redundant letters in a word. So what we had actually, we had hey Jude, right? So it has deleted all of the redundant characters. So we had 2e, right, in hey and Jude. Now we have one e only, and that's it basically. So we still have the h, the j, of course, d, e, u, y, and the exclamation mark. The same thing for smooth criminal. So you will end up by the unique characters in that word or sentence. All right, finally, you can create your own module. You can create your custom module. You can create it and you can call it to other programs, right? So let's try to do that. Let's do nvim m5.haskell. And here, let's say, let us create our custom module. Awesome. Let me actually call it custom, right? Because I'm very creative, of course, as you know. Show even, that's the name of the function that I want. So just make 2 spaces, right? The second function is show boolean, where we'll say here show even takes an integer and returns bool, and show even actually x equal to do, and we will check out if the x with the remainder of 2 is equal to 0, then this is true, else that is false. Then show boolean takes bool and returns int, and show boolean also will take an arbitrary variable, that's c, equal to do, and we will check out if that c is equal to true, we will return then 1, right? So that's going to return 1. So if it's true, we return 1. If it's false, we return 0. So we have here our custom module with 2 functions, show even and show boolean, where we can change this a little bit. So let's actually delete that and let's make it this way. So we'll check out if x right, then true, else is false. Then also I will get rid of the do part, right? We'll check out if c. All right, let's try that out. You know, everything that's related to indentation in general in Haskell it's pretty hectic. I hate it, to be honest. So let's try that again. We shouldn't. Okay, so that's good. Output was redirected with the output, but no output will be generated, of course. So this is the thing that I'm looking for, that We have our module, it doesn't execute anything. We need actually to utilize it in another program. So let me go to the interpreter again and wait, hold on. Do we have, so we have, okay, so it has compiled successfully. So let me go to the interpreter. At least we know that our custom module has been compiled successfully and we can utilize it. So if I will do load custom, no location info, yeah, that's what I was afraid of. So let me actually, okay, so let me actually create this folder. I'm going to, okay, so I need that one, right? Because I'm going to recompile everything. I'm going to copy the m5.haskell to the custom folder. Oops, let's go to custom. Okay, so I'm going to compile everything again. So GHC, yeah. All right, awesome. Now I have everything. So if I will go to the interpreter and I'm going to load the m5.haskell, awesome. You can see here that compiling custom and one module loaded, and you have here your custom module loaded in your interpreter. Great, let's check those functions. So I'm going to print show even, let's say 4, for instance. That's true. Let's check out the show boolean. Show boolean, let's say true. That should return 1. And if false, that should return 0. Awesome. And if we'll do here show even 5, that's false. So you see, we have actually created our own custom module. We have loaded it, and you know, we are utilizing the functions that we have defined. So yeah, that's everything basically that I wanted to share with you guys regarding modules in Haskell. In the next lesson, we are going to check out input and output in Haskell. Thank you so much guys for watching, and I will see you in the next lesson. Hey, what's going on everyone? This is Big Breeze channel. My name is Amir. Good morning, good evening, wherever you may be. All right, welcome to a new Haskell tutorial where we're going to study input-output. So far, everything that we have discussed or studied are static in nature. In this lesson, or in this 5th chapter, we're going to learn how to communicate dynamically with the users. We're going to learn how to write to a file, how to read from a file, and also how to handle error exceptions. So these are the main 3 things that we're going to be studying today. I'm going to switch to Ubuntu here. All right, and let me go to home. Let's go to Haskell.tut. What do we have? We have different lessons, right? Today we're going to check out lesson number 5, and it's empty, of course. And tell you what, let me go ahead and open this with Visual Studio Code. I'm going to create input-output folder. In that folder, I want to, maybe we can create 2 different files, L1 and L2. All right, so L1, L2. L1 is going to be to demonstrate how we can read from a file. For that, by the way, also I want to create a file. Let's call it file, because I'm very creative, as you know, file.txt. All right, so that's it. In that file, I want to write whatever. So let me say here, for instance, Haskell is great. I love Haskell, Rust, Python, Go, and Node. All right, so a simple text file. In Haskell, you can actually read the contents of any file that you have. So we have here a text file, so we're going to read from a text file. You can read from JSON files, you can read CSV files. So yeah, just for the sake of simplicity and demonstration, I'm going to show you only on that file.txt. All right, first of all, we need to do main equal to do. Then I'm going to create that file variable, declare that file variable, and it's called file.txt, right? So this is our file. Then the contents of this file are going to be read from that file.txt. right? So there is a method called read file. And what do we want to read? We want to read that file.txt. Finally, I want to, display everything. So you can do display text or put stir line, whatever you want. So there are different methods to display things. So we're going to go with the put string or put stir line contents. So let's go ahead and compile that l1.hs. L1. Let's run L1, and we have indeed everything that we have written. Haskell is great. I love Haskell, blah, blah, blah. Now let me show you if you want to write to a file. Instead of creating, manual txt files, you can actually create or, generate a file using Haskell code. So as always, main equal to do, and I want again a file, and I want to create this file, right? So you can give it the name that you want. Let's say, for example, games, right? Games.txt. So this is our file, okay? We haven't created yet. We're going to create it now. How to create it? By a function called write file, okay? So we have read file and we have write file, okay? These are the different input-output methods that Haskell actually grants you to do different operations, input-output. So we're going to use the write file method. So I will say uncharted 4. All right, so I'm going to save that. And finally, don't forget to read the file. Okay, we're going to read everything from that file. And let's compile that. So GHCI l2.hsol2. Awesome. Now take a look when I will run the program on the left side. You see that? We have actually generated games.txt. The idea exists in a lot of programming languages, of course. So, but as Haskell is a bit different, it's a functional programming language, so everything is about Haskell. I'm putting this, sugar around it. Because I personally love Haskell very much, even if I know that I will never work with Haskell in a company or, I've read in Stack Overflow survey. Let me show you this real quick. You see, Haskell is 2.09% among what? Among programming, scripting, and markup languages. So all respondents. So let's see professional developers. In which position Haskell is. So search for Haskell. Right, 1.8%. So yeah, it's even below Perl and Objective-C. It's even below VBA. Can you imagine that? That's a shame. Learning to code. Okay, hopefully that's going to be a bit higher. Haskell 2.51. No, still low. Alright guys, with that, shut the video and do not watch any of my Haskell tutorials anymore. No, I'm joking. We are learning just, for fun. Let's see also where Haskell lies. So, Haskell here, okay, 2022 median yearly salary in US dollars, 80,000. That's relatively low, but that's not very low compared to C#, for example, in 2022. In 2023. Okay. Yeah, but if you will compare that to, but that's really odd. It's higher than Python. It's higher than Python, or maybe I'm mistaken. So take a look. It's 85,672 in 2023. Let's take a look to Python. 78,000 yearly. Right, so you see Rust and Haskell, they are close to each other, which is quite interesting in terms of salary. Go is higher, makes sense. Erlang, Lisp, Scala, Clojure. Right, so yeah, this was a little bit of a distraction, guys, but what I want to tell you here is that learning is good. Even if you will not use it in a direct way, but enriching your knowledge is something that you can do for your own good, believe me. All right, enough me yapping, let's continue. So if we'll go to games.txt, we have everything that we have actually written in our Haskell file. Right, the last thing that I want to show you is how to handle exceptions. Okay, so like that, and let's go to our file, let's close that, All right, an exception can be considered as a bug in the code, right? Any exception that you can have, it will jump in your face, and I'm quite sure that you have encountered the situations tens of times, if not hundreds of times, that you have an error or a bug in your code. So it's a situation where the compiler doesn't get the expected output at runtime. That's why it generates this exception or this error. Let me show you how to handle exceptions. So in Python, for example, you have try except, right? In JavaScript, for instance, you have try catch, right? To catch any errors. In Rust, that's cute. You have result that will result in OK or the error itself. And there are other ways in Rust like unwrap, expect, panic macro. So yeah, in Haskell, that's no exception, no pun intended. So let's go ahead and see how we can handle exceptions in Rust. So first of all, I will need to import the exception from the control actually. Okay, module. That's the first thing. Next, then we'll do main equal to do. Then I want the result. Now I will try to see if I will divide 10 by 0. It will, of course, result in an error. But how we can catch that error in order to not, generate that exception error in our code? We're going to evaluate, but before that, we're going to wrap the evaluation in try method. So that try is going to, wrap that evaluate method, which is evaluating. Maybe I can do like this because it keeps bothering me. We can evaluate the division of 10 by 0. So you see here we have our try method that's going to, examine the evaluation and will, return some, and will return a result based on different scenarios, if the division is okay or the division is not okay. And here I want this from IO and either some exception integer. Now I want that case result of different scenarios. First, left. So we'll say here the error or the exception. So we can say that this is the exception, and that's going to put stir line followed by $, and we'll say here error caught. Or can make like this because we're going to display the error, the type of error itself, division by 0 error or whatever. And we will just concatenate the exception itself, right? And in case of correct calculation, so that's going to be the right, that's going to be the value itself, and here we will change the display message. We'll say the correct answer is, and whatever, and here we'll change that, of course. All right, so this is simply our try mechanism to catch any exceptions in Haskell. Let's go ahead and try that out. Let's run and see if we'll get any errors. Yep, error caught, divide by 0. Now if I will change 10 to 2, for instance, and let's compile again. Let's run that again, and we have here a different outcome. The correct answer is 5. Alright guys, so this is the end of this video. We have studied how to read from a file, how to write to a file, and how to handle exceptions. Thank you so much guys for watching, and I will see you in the next video. Hey, what's going on everyone? This is BigBrace channel. My name is Amir, and welcome to a new Haskell tutorial. So far we have studied a lot of concepts in Haskell. Now, functors in this book is chapter 5 or 6. And again, this course is not going to give you everything you need to know in Haskell, but in my opinion, it's going to pave the road for you if you want to learn more about Haskell programming language. So it's going to open your appetite, if you will, to learn more Haskell. All right, so let's go ahead and start our lesson. Today's lesson is about functors in Haskell, as I said. So let me just open my Visual Studio Code. So what's remaining in this course actually are 4 chapters: functors, monads, monoids, and zippers. Right, so for functors, I'm going to just create main.haskell. And here I will type functors. What are they? All right, so let's talk a little bit about functors or functor. So functor in Haskell is a way to apply a function over different data types like lists, maps, and trees in Haskell. So functors are defined in Haskell with a class that includes a key function called fmap. So that's the most important thing you need to know, the fmap. So the fmap actually is a method that takes a function from A argument to B argument and a functor containing A. So let me give you an example and show you how a functor works with the fmap. So I'm going to use the keyword class to define a class, and that's a functor with F capital, and that's going to be F, where the fmap here, and that's going to take A and return B. That's going to take F A and change it to be FB. Right, so let me just explain that for a moment. So what happened here is that this fmap function or method is going to take a function from A, so it's going to take from A here, right, to B. And it's going to apply the function on or to each element FA and will return a functor containing B. So don't forget that this F is the functor. So it's going to take the A and it's going to apply this function on each element in that A, and it's going to return a functor that contains B. I know this is a bit an abstract, not so clear theory, but once I'm going to show you a practical example, you're going to understand what fmap is and what's the difference actually between fmap and map. I'm going also to talk about that. So for example, if you have a list of numbers, 1, 2, 3, 4, whatever, right? You have a list of numbers. So you can use fmap to apply a function to each number to that list without unwrapping anything. You don't have to unwrap anything from the list. It's going to be injected and, change or do the polymorphism on that list. So let me give you a practical example now. So that's main do as always, and here we can do print, and I can use the fmap, and I'm going to subtract. So subtract 1. So we're going to subtract 1 from that list containing 2, 3, 4. We can do 2, 4, 6, 8, and 10. All right, just minimize this a little bit. Right, and you can do the exact same thing, but instead of the fmap, you can do it on map. Now we're going to get the exact same result. Let me show you if we'll open the GHCI, the interpreter, and what if you will type fmap. It tells you here that no instance for show A0 to B0 that takes the A or to apply the F on the A and returns the F with the B. It changes the A to the B using that functor. So what we can do is we can write fmap, and I can type here multiplied by 2, for instance. So we're going to take number 2, we're going to apply the multiplication of that number using the fmap to a list. So if you will create a list here, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, close the list, hit enter, it has actually applied the multiplication. It took number 2 and it has multiplied it over the whole list. If we'll do map 2 to a list of 1, 2, 3, for example, and if you will use map only without fmap, that's going to do exactly the same thing. That's taking multiplication of 2 and applying it to the elements in that list. So here we can have a conclusion that fmap and map work or behave the same. On the list. However, if we'll have other data types other than list, the behavior is going to change. So let's say, for instance, that we have other types like maybe, right? Now, maybe is not going to work with map. So you need to know that fmap and map work the same on list only. That's the only case in Haskell. When we'll have different data types like maybe, now the behavior is going to change. Take a look. So let's take fmap and do +5, for example. And I'm going to wrap the number 10 with just. So I want to return if that number exists, if that number is true, I want to return 10 plus 5. Take a look, it's going to give you just 15. However, if you will do fmap and you will add any number, on nothing, that's going to give you nothing. So the fmap is going to be applied to the same function with whatever the number that you want, but now to nothing instead of just. And since there is no value inside nothing to apply the function to, the fmap returns nothing. Now you can do that with map, for example. You will get an error, either with just or nothing. It's going to give you the same error. Doesn't work with maybe, right? And you can do whatever you want. You can do, for instance, division 2, just 10. That's going to give you 5. So this is simply a functor. And also it works on trees. But the other thing that I wanted to show you is the applicative functors. So applicative functors allow functions wrapped in a context, like maybe, for example, to be applied to values in a similar context. So let's say we have here a class. Here functor f, and that's going to return applicative f, where now we have here pure a, and that's returning f a. And this simply says that pure takes this value and wraps it in the applicative context. And this pure right here takes a value and wraps it in the applicative context. It's used to lift values into the functor, actually. So this is as far as pure. There is also sign written like that. So this actually applies a function in a context to a value in that context. So the way to write that, it would be, would be like this. So let's do it. So let's do like that. Yep, instead we have here f, and we'll have the exact same thing like we have done here in the original functor. These two brackets with the asterisk, let's call it Nemo, for example, right? Nemo takes an applicative functor that contains a function, the f, with the a returning b, and another applicative functor containing a value f to the a, and applies the function to the value, all within the applicative context. I know, again, this is abstract. Let's go to the interpreter and show you so you would understand better. So first of all, you will need to import the control applicative module. So control.applicative. This is going to provide the applicative type class and the associated functions with it. And this is actually going to help me very much because I will need to create a function that's called f1, and that's going to take two integers, x and y, and it's going to do some calculations or computations. It's going to multiply 2 by x and add to it y. Now I'm going to use the applicative style to apply the f1 to maybe values. Both are going to be just, but the first one's going to use the fmap. It's going to be aliased with the $sign, by the way. So this is actually fmap. Okay, this is an alias for maybe in Haskell. And it's going to result in a function wrapped in just. The other one is going to use the Nemo. I'm going to apply this wrapped function to just 2. So we'll have just 1 and just 2. We're going to use the applicative operator Nemo resulting in just. We'll see. Show with the maybe, and we'll have here f1. Then we'll have maybe, but the first case is going to be just 1. The Nemo here for just 2. 2 multiplied by 1, that's 2, plus 2, that's equal to 4. Alright guys, so this is simply functors and applicative functors in Haskell. Thank you so much for watching, and I will see you in the next lesson where we're going to study monads. Hey guys, and welcome back. In this lesson, we're going to study monads in Haskell. Now, in the previous lesson, we have studied together functors and applicative functors. Monads actually are a type of applicative functors, but come with additional features, which allow them to handle more complex operations. So to give you an example, I'm going to create a class monad. I'm going to call it M, and that's going to be where we want to return A, returning MA. Right, let me explain for a moment. So first of all, we have declared the monad type class for a type M. Then the return statement actually takes a value A and wraps it in the monad context M. And here what it does, that it serves to lift a pure value into the monadic context. Now we have different operations. One of them is bind. Bind in Haskell is written this way, with 2 bigger than sign and equal. This is bind, or pronounced as bind in Haskell, and this actually takes a monadic value and a function that takes a normal value and returns a monadic value, then applies the function to the unwrapped value from the first monad and returns a new monad. I know this sounds complicated, trust me, it's not. So everything that I've said, I'm going to write now. So we're going to take a monadic value and a function, and it's going to apply a function to the unwrapped value from the first monad and will return a new monad. So returning a new monad in form of MB. Again, all this is theoretical. If you know algebra, I think this is going to be very clear and understandable to you. If you come from Python, JavaScript, Java background, this might seem a bit odd and, weird and maybe annoying, but I'm going to do my best here to make things easier and simpler for you guys. Again, this course is not intended to make you a solid Haskell developer. I'm just exploring or discovering things in Haskell, and I'm sharing with you. And I said, instead of putting those separate videos, I will create a course or a Haskell course for beginners, so they will understand what these things or why these things are called this way: monads, functors, monoids, zippers, and so on. The next operation we have is pronounced then. So we have bind and we have then. Then is done like this: 2 bigger signs next to each other. That's it. And this is used to sequence 2 monadic operations where the output of the first operation is not needed by the second. So this is written this way: MA returning MB, and we don't need the A anymore, so that's going to be MB only. And just to give you an example, you can take the X, then Y equal to X, binding with /_ returning Y. This is actually syntactic sugar that simplifies chaining monadic operations, ignoring the result of the first. And finally, we have fail. Now, fail provides a mechanism for error handling within monadic computations. So you would do fail, and whatever the string is, returning MA. So you can say here, for instance, fail message, that's going to be error message. So the monads actually follows three laws of monads. The first law is called the left identity law, and this simply means wrapping a value with return and then binding it with a function should give the same result as just applying the function. Okay, mathematically it should be like this, return A binding F. This is the same as you would do FA, exactly if you would do like this. Okay, so that will wrap a value with the return and then bind it with a function which should give the same result as just applying the function like that. So both are the same actually. The same as. Okay, so this is the left identity. This is number one. Number two is right identity. And the right identity law means binding a monadic value with return should not change the value, should not alter the value of that variable. And mathematically, it's written this way. And that's going to be exactly the same as with the x. It's not altered, the value is not altered or changed or anything. Right, so you can do like that. The same as x, value not changed. And the third law is associativity. So the associativity in monads means the way in which functions are chained together doesn't change the outcome. And mathematically, it should be written like this. We have here M binding with F, for example, and that is binding to G. So this should be the same as if you would do this way. M binding to / x returning fx binding to G. And I know all of that theoretical, guys, and better to show you some examples. I'm going to show you first the left identity law. And again, I'm going to define it very quickly. So this means that if you put a value into a default context with pure, in older Haskell code, this is returned, by the way. So simply means that if you put a value in default context with the pure statement and then apply a function, this should give you the same result as just applying the function directly to the value. So let me give you a practical example. Let's do return 3 bind with the / x, and that's going to return just x plus let's say 122 or whatever. And you can see that it has added just 125. It has added 122 to the 3. And if you would do it on pure, that's going to be the same thing. Pure and return do the same thing, but return, that's older Haskell code. Okay, so this is the left identity law. The right identity law would tell you, hey, if you apply the bind to a monadic value m, let's say, and the function pure, you will get the original monadic value back. So you can say, for instance, just 5, and you will bind with pure. And again, if you will do return, that's going to be the same thing. This simply means that just plus bind sign return the original monadic value. It will not change it. And the last law, which is the most complicated, is the associativity law. In associativity law, the way functions are working, that they are nested with the bind sign, and this actually doesn't change the result. So if you're going to nest the functions with the bind sign, the result is going to be the same. Let's define function. So that's f function, that's going to take x, and it's going to return just x plus 1. And we can do the same thing on a different function. Let's call it g, for example. It's going to take x again. It's going to multiply this by 10, for example. So if you would do just 1 binding to f that binds to the g function, you'll have just 20. Why? Because first of all, just 1 plus 1 equal to 2, and then in the J function, 10 was multiplied by this 2 to give you just 20. You can do it differently. You can do just 1 binding to with the backward slash x, and that returns function taking x binding to G function. That's going to give me just 20 as well. That's going to work exactly the same. Alright guys, so this was Monads explained briefly in Haskell. Thank you so much for watching, and I will see you in the next lesson. Hello guys, and welcome back. In this lesson we are going to study monoids in Haskell. So in Haskell there are a lot of laws. We have seen the last lesson for the monads, and do not confuse monoids with monads. We said that a monad class has 3 laws: the left identity, the right identity, and the associativity. So what is a monoid? A monoid is a type class that is equipped with a binary associative operation, mappend. M stands for monoid, so mappend means monoid append, and an identity element which is empty or monoid empty. And these components must satisfy 3 laws: the identity law, the associativity law, and the closure law. So 3 laws must be satisfied with the monoid components. So let's read what we have. This is a wiki, by the way, wiki.haskell.org monoid. So it tells you here that in Haskell, the monoid type class, so we know now that monoid is a class. And to not be confused with monads, that's what I told you. This is a class for types which have a single most natural operation for combining values, together with a value which doesn't do anything when you combine it with others. This is called the identity element. And this is one of the laws: the identity, the associativity, and closure. So let me give you a very simple example to understand what monoids do. So first of all, I'm going to define a new data type called myString. So I'm going to define new type that's going to be called myString, and that's equal to myString, right? This is a string data type, and that's deriving, show, and equal. So next I will implement the monoid instance. So I'm going to make myString as a instance of monoid, and we're going to define empty as an empty string and mappend as string concatenation. So we're going to create instance semi-group like that. MyString where, and maybe I can just minimize this a little bit, right? Where myString x is not equal to myString y, and that's equal to myString x plus y. And now I can actually create the myString to be an instance of the monoid. So monoid myString, right, where empty is equal to myString. So let me define different variables. S1, that's going to be take myString, which is the instance of the monoid, and it's going to have here hello with a comma. And you need another one, that's S2, and instead of hello we're going to say world, and the last instance that's going to be S3, and we're just going to leave it an empty string. Now I will show you how to use the mappend, and it is translated this way. So we're going to print S1 mappend S2. This is going to return the string hello world, right? We're going to put hello and world, the S1 and S2 together. Now the idea of the monoids, I think, started to be clear. That's for the mappend. I can also test the ID or the identity property. And the identity property, I'm going to use the mempty here. So let's take a look to that. That's going to be interesting. S1 mappend with mempty. And this should display my string hello, right? If we'll do the same thing, just keep it like this. And here is S2. This should display my string world. And then finally, I want to test the associativity. So testing or test associativity. So I'm going to print, here we'll say S1 mappend S2, and that's going to be mappend to S3. And we'll do this differently. We will do S1 outside of the brackets now, S2 with S3, just like that. You can do it differently. You can put the S1 outside of the brackets, just clean this a little bit, just put this brackets like that, and you should be good. That's going to display the same thing, hello world. Now let's go ahead and compile that to see how monoids work. Let's actually quit the interpreter and let me do GHC. The name of the file is main.haskell, and I want this to be an executable, an output file under the name of main as well. I think we have a problem. Okay, let me just minimize this a little bit. Yeah, oh, I forgot actually to append, right? Okay, so let's compile that again, and we shouldn't have any problems. Awesome. Now, if you will take a look, you will find we have our 4 files, and of course we need to run the executable. So the first one we have here, hello world, because we have appended S1 with S2 with the mappend. Next, we have only my string hello and my string world, because we have appended the mempty with S1, and the next example with the world, we have appended the mempty with S2. Now, the last examples, basically they work the same, but they are done differently. We have tested the associativity, where we can put the S1 appended with the S2, appended with an empty string, which is S3. All right. And we have done that differently by appending the S1 with the S2 first, and with that appending the S3. The second or the final example, we have actually appended the hello with the world and empty string together, right? And we had the same exact result. All right, guys, so that was it. This is Monoids explained in Haskell. Thank you so much for watching, and I will see you in the next and final lesson with zippers. Hey, what's going on, guys, and welcome to the final lesson in Haskell course, which is zippers. Thank you so much for watching. I hope the course has been useful to you so far. Now let's talk about zippers. Zippers are a fascinating data structure used in functional programming in general and in Haskell specifically to efficiently navigate and modify data structures like lists, trees, and many other. So here I'm going to provide an overview and a simple example of a list zipper in Haskell. We're going to write the code for a Haskell file, and we can compile it later. We're not going actually to open the interpreter. But let's take a look to what the wiki says. The zipper is an idiom that uses the idea of context to the means of manipulating locations in a data structure. Zipper monad is a monad which implements the zipper for binary trees. So first of all, I want to define the list zipper type. So I'm going to say type list zipper. That's going to be called A, and that's equal to, we'll open parentheses and just square brackets. We'll put here A and A. This is how to define a list zipper type. Next, I want to move the zipper to the right. So I'm going to create this function called goRight. So goRight here is going to take the list zipper A, and it's going to return, maybe you can just minimize a little bit. It's going to return maybe list zipper with the A. And I can take go right again, because what I want to do is simply moving the zipper to the right. So the go right actually is going to take left and X set to the right. I'm going to delete everything just here with X set to the left and right. And finally, I'll do like that. And that's going to be equal to nothing. Now I will do the exact same thing, but instead of the right to the left. Let me just modify the comment here. Move the zipper to the left. And we'll change things here. That's going to be X to the left. And here we'll say from the right. So from the right to the left. And that's going to be just left. And here going to be X set to right. And I'm going to start with the focus on the first element. So I'm going to set the zipper to be equal to, that's an empty list first. Then I will have here a list of numbers, 1, 2, 3, 4, 5, 6, whatever. Then I will guide the user to tell him that this is the original focus. So put stir ln. Next, I will just show the current focus, which should be just 1. That's not the original focus now. This is after moving to the right. So after, maybe you can just delete the whole thing. After moving to right, and that's going to be after moving to left. And I will print with the $sign. And here I'm going to use the fmap. You remember the fmap from the functor lesson. Focus, and I'm going to use go right zipper. So go right zipper. And this is going to be after moving to the left. Now, the way to do that is going to be not as simple as you think. You might think, okay, I'm going to change from go right to go left, but we will not do that. We actually want to move right, then left, and show the focus. So the way to do that simply is by leaving the go right zipper as it is. And we're going to bind, if you remember from the previous lessons, we're going to bind to that go left. This way we're moving from the right to the left and leaving the focus on the left side. That's good and all, but we will need to create this focus, right? So let's get up here and let's actually create this function to view the current focus of the zipper. So let's actually try to implement that. So that focus, that's the name of the function, that's going to take list zipper A and return maybe A. Next, I want to check if right list is empty, there is no focus. So we'll do here focus and just like that. Here empty with empty list, and that's going to be equal to nothing, right? And I want to put the focus, which is going to be the head of the right list. Focus here is underscore, X is set to underscore as well, and that's going to be equal to just X. All right, so this was the only thing that's remaining for us. Right, awesome. Now let's go ahead and compile our code. So I'm going to use the Glasgow Haskell compiler, the main.hs. I need an executable file, and I will call it main. I will not change anything. Awesome, that has compiled perfectly. Let's check what we have. We have our executable, our interface, our Haskell file, and the output. So let's go ahead and run our executable, and you can see that the original focus, just 1, after moving to the right, just 2, and after moving to the left, just 1. Right, so that's the main idea of zipper and how zippers work in Haskell. Yeah, so that wraps up our Haskell lesson and the entire Haskell course. Thank you so much, guys, for watching the whole course. I hope this has been useful to you. I hope this has given you a gist of what Haskell is, how Haskell programming language operate, And hopefully it will open your appetite to learn more about Haskell. Again, thank you so much guys for watching, and I will see you in the next course. Till then, stay safe and be well. See you later guys.